There's neutrinos, the masses, and it can be divided by the neutrino relations. And the smallest of the neutrino mass is usually explained by the extensions of the standard model with the allowing sort of the Manara mass term that's to make the Lipton number violations. And in this case, the Yukawa matrix is different with the other fermions. So there's some additional heavy minor neutrinos added. So the parametrization of the Yukawa matrix should be different. So both of the Lagrangian neutrino mass can be written like that. The first term is the Yukawa coupling term, which gives the Dirac mass term. And the second term is the Manara mass term, which gives the some Lipton number violations. To talk this size of the matrix, so we will set the there are two right-handed neutrino. That are some of the minimal extensions of the right-handed neutrino. So it is called the 2RHN model, two right-handed neutrino. And in this extensions, the Manara mass matrix is a 2 by 2 diagonal matrix. And the Yukawa matrix term becomes a 3 times 2 because the active lap-handed lepton is the 3 vectors, and the right-handed neutrinos are 2 vectors. And we want to parameterize the Yukawa matrix with satisfying this diagonalizations of the active neutrino mass matrix, and such a diagonalizations of the neutrino mass is determined by the mixing matrix, so-called the PMNS matrix, and it coming from the oscillation data. And also the some of the mass eigenvalue sort of the active neutrino mass is also determined by the oscillation data, mass scale difference. So such as some of the satisfying the neutrino oscillation data is important when we consider parametrization of the Yukawa matrix. So such as mass scale difference determine the eigenvalue of the neutrino mass matrix, and the mixing angles determine the eigenstates or mixing components of the neutrino mass matrix. And the answers of the parametrizations of Yukawa matrix is the Casas-Ibarra parametrization. This the important formula in this talk. So the Y new is Yukawa matrix, and the U is the PMNS matrix, 3 by 2E matrix, and the M new is the diagonalized neutrino matrix with the 1/2, and O is the orthogonal complex matrix in with the 3 by 2 matrix. It represents some mixing between the left-handed active neutrino and the right-handed external neutrino. And there also having neutrino mass matrix diagonalizations through the inserts and over the Backward values of the Higgs field. If we use these parametrizations, then it might there's such a mixing matrix convert between the Bleiber's eigenstypes of the neutrinos and the mass eigenstype in the Lagrangians. Also, it can satisfy the seesaw mechanism, such a relation. Active neutrino mass is determined by the Dirac's and two Dirac matrix in the numerites, and the Manara mass matrix in the denominator. Also, matrix multiplications is all consistent. That is a relation. So we will check about the such a Casas-Ibarra parametrizations is consistent with the all the Lagrangian, like as some of the mixing between the Bleibers and the mass eigensize and this is a relation. And after that, we will derive the Casas-Ibarra parametrizations and check about what is the meaning, so especially that this matrix O. The matrix O is actually the some mixing between the left-handed and right-handed neutrino. So the first, the consistency, we will discuss about the direction from the Yukawa matrix to the Dirac mass matrix. So this is the Yukawa mass matrix. In this case, the Higgs get the bulb. So Higgs double get the bulb. So the neutrino parts of the lepton double lasses appear, and it becomes the Dirac mass matrix. And if we use Casas-Ibarra parametrization instead of the such a Yukawa matrix, instead of such a Casas-Ibarra parametrizations in the positions of the Yukawa matrix, then first of all, such a PMNS matrix converts from the Blevers eigenstate to the mass eigenstate. And second, the Higgs bulbs in the numerator and the denominator is the offset. And the active neutrino mass matrix here, using the Caesar relation, we can write like that by using the Caesar's relations, and all the mass matrix are diagonalized here. And because right hand is a mass and the mass matrix is a diagonal, so we can commute the order. So the such a mass matrix is the opposite in the denominator and numerator, and it becomes the Dirac mass matrix will disappear. So from the Yukawa matrix, the Dirac mass matrix can be obtained. In the opposite direction, from the active neutrino mass matrix to the Dirac mass matrix. That's active neutrino mass matrix, and that's a Casas-Ibarra parametrization. Active neutrino mass matrix can be represented in terms of the Yukawa mass matrix, the inverse of the Casas-Ibarra parametrization. And by using the definition of the Dirac mass matrix, multiplications of the path and the Yukawa matrix becomes the Dirac mass matrix. So such new active neutrino mass matrix can be represented like that. So instead that's the thing, and by that, there's a scale because here is the nu 1/2 and there's the nu. So the one mu part and the second mu part and the O is the orthogonal complex mass matrix. So this becomes the one, and by that also PMNS mass 3U changes the from the mass against the Blevers eigenstate. Note that the U dagger changes the Blevers eigenstate to the mass matrix because the U makes the diagonals the mass matrix. So it is consistent because that's a Blevers eigenstate mass matrix in the Blevers basis, and this is the mass matrix in the mass basis. So the Blevers eigenstate can be represented as a U, nu arm, and also for the joint spin, it is represented as a nu alpha bar is equal to the nu arm bar u dagger. So it becomes MD Dirac mass matrix MR inverse and MD transverse, so it becomes active neutrino mass matrix. So all is consistent. So now let's derive some Casas-Ibarra parametrization. That's the same Lagrangians we saw in the previous slides, and below this Laplace. And yes, the active neutrino mass matrix can be diagonalized using the PMNS matrix, and the Manara matrix is already diagonalized. And that is the Casas-Ibarra parametrization. We already saw in the previous slides, and the derivation is given like that. So consider that this diagonalizations of active neutrino mass matrix. That some diagonalized mass matrix and new by these relations, it can be written like that. with the minus sign. And because the heavy neutrino mass matrix is already diagonalized, so we can decompose with some root of the Mn, roots of the Mn. And also in the left-hand side, the M nu is also diagonalized. It's the root of the M nu and root of the M nu, and it can be go to this right-hand side. So only the ones that remains in the left-hand side. So M nu inverse and root, mu inverse and root. So there are two similar forms that appear. So there are mu PMNS matrix V, MDMNS. So on the left hand side is the ones, and this part and this part is conjugate each other, so we can define that this part is R and this part is R daggers, and the R daggers are satisfied the one, and R is actually the orthogonal complex matrix, so we still see it as an O, the notation as something different. Also, V is a PMNS matrix, we saw that as a U. So the by the rearrangement of such a term, this R, then such a Dirac mass matrix can be represented like that. That is actually Casas-Ibarra parametrization, because that is the V root 2 times the Y nu. There's the I factor because there are minus signs in the relations, and the root Mn orthogonal matrix R and the M nu roots and the PMNS matrix V. The meaning of the R is that shown like that. There are some of the mass matrix in the left-hand and right-hand chiral basis. And such a diagonalization of the mass matrix that R appears in the off-diagonal terms. So it is actually the mixing between the left-handed selective neutrino and the right-handed sterile neutrino. So flavors the mass eigenstype can be written as mass eigenstype and the PMNS matrix, and because there are some extensions with the additional right-hand neutrino, so right-handed neutrino contributions are represented like the R. So R is actually the like the theta 1 Bose thing as the active sterile neutrino mixing. So such as some of the Casas-Ibarra parametrizations is used to talk to some of the leptogenesis. So because there are some heavy neutrinos that decays into the leptons and the scalar Higgs thing, and such a decays are determined by the Yukawa matrix, and the important quantity CP symmetry epsilons that are related with the imaginary parts of the Yukawa matrix. And such a Yukawa matrix can be parametrized by the such a Casas-Ibarra parametrization with various some parameter, especially in the orthogonal complex matrix O. There are some undetermined mixing angle jet, and it is also same as R, which is the mixing between the some active neutrinos and the sterile neutrinos. So the Casas-Ibarra parametrizations, the importance to analyze some of the heavy sterile neutrino and especially the leptogenesis.